So we're going to talk about conservation of mass, and this leads into us understanding how chemical reactions work, and I just realized that my screen's not on. Okay, so conservation of mass is today's topic. Can you guys see that color? Excellent. Now, all colors are equal. So the first thing here is this. One, in a chemical reaction, no mass is ever created or destroyed. Okay. So, as a quick example here, say I have a beaker, or an Erlenmeyer flask, I guess. It's a little ugly, but whatever. And the example that we did was we added an Alka-Seltzer pill into some water. We noticed that bubbles kind of effervesced up, okay? And we also noticed that if we were to weigh, the pill and the water in the flask beforehand, and we were just allowing the gas to escape into the open air, that over time, the overall mass of the system would drop, okay? So that was Exhibit A. And then tried a similar experiment, except this time, right, you put a balloon over the top, fixed it on there, and you had put the pill inside the balloon, and then you allowed it to fall inside into the water. In this scenario, hopefully what you noticed was that although you maybe did not have a perfect retention of mass, because there might be some leakage, you probably noticed that mass barely changed, okay? Mass didn't change. So this is just an illustration of the fact that even though apparently sometimes in chemical reactions, and lots of chemical reactions, mass disappears, in reality, it's been proved over the last few centuries that mass is never lost, okay? Now, when people were sort of arguing about, the fundamentals of chemistry way back when, and they weren't really sure about what was happening with mass, they had theories like the phlogiston theory and so on, which we talked about, where as you burn something, right, phlogiston, this mystical heat liquid, it leaves, right? And if you weigh the ashes after a fire is burned, you're going to find that they weigh less than the wood, right? We understand today one of the main reasons why that is because one of the products of burning is CO2 and another one is H2O. We'll get into that a little bit more. So these are, fairly hefty chemicals, and what's left behind after is, basically trace minerals and so on that were inside the wood, and that's what makes up ash, or maybe some unburnt carbon and so on. But most of the mass has left, okay? Now the question is why? Why is it that this happens? Why is mass not created or destroyed? And maybe not why. Why is kind of a tough question to answer, but how do we understand this? Why is mass not created or destroyed? Or how do we understand the fact that it's not created or destroyed? Well, when we think about what all matter is made up of in the universe, what do we say? What is all matter made up of in the entire universe? I'm giving you a hint. I'm pointing at something that's on my wall over here. Elements. Good. Everything has to be made up of elements, and we know that elements can be, broken down into their smallest form, which is the atom, right? So all matter is made of atoms. And under normal circumstances, you can't create or destroy atoms. They're like the fundamental building blocks of everything around us, okay? So in a chemical reaction then, what we have is we have a shifting or a changing of atoms from one compound to another, or from elements to compounds, or from compounds to elements. Okay, so an example that we're going to do tomorrow is what happens if we were to take two types of gas, hydrogen gas and oxygen gas, and we were to apply a little bit of heat. What do you think, what do you suspect the product of a reaction that looks like that would be? Hydrogen and oxygen. What famous chemical has hydrogen and oxygen in it? Yeah, that's right, water. Absolutely, yeah, water vapor, that's right. Okay, and it turns out that this makes a very energetic reaction, right? The forming of the new bonds between hydrogen and oxygen releases a lot of energy, okay, and it actually makes an explosion, okay? But the thing that I want you to notice here is something about the conservation of the mass. So what I'm going to do is I'm going to draw what hydrogen looks like. So hydrogen is made up of two atoms that are linked together like that. And oxygen is made up of two atoms that are linked together like that. Okay. And if I look over here, if I combine these together, okay, we get a new situation where we end up with that and that and which color did I use? I think this one. And one of those. Okay, now if I look, did I conserve mass in this scenario? Does it look like I conserved mass? Well, before you answer, let's do some counting. There's 1, 2 total hydrogen atoms here. And there's 3 and 4, right? Because there's 2 oxygens. So if we look, there's 1 and 2, and there's 3. What's missing? What have we not accounted for? Okay, so yeah, we haven't accounted for number 4 here. Oops, number 4 here, right? So in this scenario, the way we've written this out implies that we've essentially lost an oxygen. It went away, right? We know from experimentation that if we were to do this, say, on a scale or in an enclosed, environment, what would end up happening is it would weigh lighter than the ingredients that we put in, than the reactants that we put in, right? So we have to devise a way to show that the same amount of, atoms that went in come out the other end. So that's actually for another class. We're going to learn to balance reactions. But what we need to get from this is this fact that in general reactions, we have to show that if there is a product, okay, then all of the stuff that was in the reactant side has to show up in the product side. So I'm just going to quickly, without getting too deep into how I did it, show you what we would do in this scenario. What we would have to do is we'd have to account for the extra things that are here. So one way we could do that is we could draw 2 more hydrogens. I think I used a slightly different color than I should have. Another oxygen. So now there's that number 4. Now, we're still not balanced, but what could we do to make it balanced? What could I add in? Yeah, absolutely. So if I put another H2 in, I think you'll see if we say apply some numbers here, 3, 4, 5, 6, 5, 6. Now what we see is this side and this side are balanced. Okay, I'm not really going to get into balancing. The whole point is that we talk about conservation of mass. But if we understand matter in terms of atoms, then the reason why mass is conserved makes sense, right? The atoms realigned who they're partnered up with, okay? However, no new atoms came out of thin air, and no atoms were destroyed to disappear into thin air. Does that make sense? Okay, sweet. And then, yeah, question. Yes, that's right. So it's H2O because there's 2 hydrogens and 1 oxygen. Okay, and we'll review what a chemical formula means before we get too far into this. And all we would do to show this would be this: we put a 2 there, and we put a 2 there. Okay, we'll review balancing next class, but I just want to make sure that you understand this concept that in a reaction, no matter is ever created or destroyed. Okay, this is the law of conservation of mass. and it comes from Antoine Lavoisier, and we're going to watch a quick movie about his life.